Greetings. Today we shall discuss intracardiac echo in ablation. The objectives for the talk are to see what views are used to map the atrium, the ventricle, how does the intracardiac echo help in transeptal punctures, cavo-tricuspid isthmus evaluation, and management of outflow tract pathology. So, all the catheters offer a phased array technology in their intracardiac echoes, which allows for detailed visualization of anatomy due to its close proximity to cardiac structures. It also delivers a farther depth of penetration. There is a ease of use since an alternate operator is not required, and it provides us real-time feedback. These are the typical views that we see. With the probe placed in the mid-right atrium, we can see the right atrium, tricuspid valve and the right ventricle. This is usually the home view. We come back to this whenever we get lost in the heart. And then once we clock from here, we are starting to see the left atrial appendage, the mitral valve, the right atrium and the left atrium. Now, important to know that since we are in the right atrium, we need to see this space before we are moving the catheter. If we are showing proximity to tissue, it means that we are very close to tissue and can perforate with the catheter itself. Moving on, another counter gives rise to the right ventricle, the outflow tract as well as the right atrium. Again, the right atrium is closest to the catheter. The tricuspid valve is seen very well here. And if you clock from the view that we saw the left atrial appendage, you can again see the left superior pulmonary vein, the inferior pulmonary vein and the left atrium here. Important to note that the left inferior pulmonary vein is in close proximity to the aorta, and that can be used to differentiate whether it is superior or inferior. We also deal with the right atrium, the aorta, the outflow tract of the aorta and the left ventricle in what is a counterclocked view showing the aorta in profile. Moving on from there, if we end up clocking any further from there, we can see the left atrium that will be seen along with the esophagus and the descending aorta. Remember, this view is after we clock from the left superior pulmonary vein and the inferior pulmonary vein. Now, clocking it further, we now start to see the superior pulmonary vein on the right side, the inferior pulmonary vein on the right side, as well as some parts of the pulmonary artery. This shows the close proximity of the pulmonary artery, especially when it becomes the R or the right pulmonary artery with the RSPV. Sometimes we can actually bend the catheter across the tricuspid valve to get a better sense of the right ventricle, and from there clocking gives us the left ventricle. Now, before a procedure, you want to kind of rule out clots within the heart. This view at the home view shows the thrombus on the lead which is placed. These are lead-based masses and are not necessarily any kind of vegetations. Similarly, if we are able to flex, enter the ventricle in an anterior location and then clock it, we can see the aorta in the cross section along with the left atrial appendage and the left upper pulmonary vein. This is also a very useful view, especially when using older catheters where the fidelity of the catheter in the image may not be very good. Moving on, we can also look at the home view, which is again the right atrium, right ventricle and the aorta, and then clock it to see some parts of the outflow tract, the aorta, and also sometimes look at the appendage. The appendage is the initial pouch-like structure above the mitral valve. During transeptal access, we can actually start to visualize it from the home view. You clock and posteriorly bend the catheter, we are able to see the septum. This is the right atrium. The SVC is here. The needle drops from there onto the septum. You can see the tenting of the needle. And then finally, once you puncture, you can see the shower of bubbles into the left atrium. This creates unparalleled safety for the transeptal puncture and also allows us to puncture at the site we want to and not at any random site on the foramen ovale. Additionally, we are also going to see how once we have the sheath within the left atrium, we can actually advance the catheter into any of the pulmonary veins, and this can also be visualized under the intracardiac echo guidance. In order to reset or set the contact force sensing, we should not be in contact with any tissue. Therefore, keeping the catheter in the mid left atrium allows us to properly zero the contact force catheter. Moving on from there, in the LA itself, we can actually visualize where it is that we are making contact. Here it is the posterior wall, here it is close to the roof, here it is on the Coumadin ridge, and this allows us to ensure that not only are we not fooled by the numbers we are seeing, especially at these locations which are very notorious for instability of the catheter, but also assess the lesion formation itself as it is happening. A corresponding view on fluoro would only give us this much information. Moving on from there, the cavo-tricuspid isthmus. Typically, the cavo-tricuspid isthmus is this way. You have the tricuspid valve, you have the cavo-tricuspid isthmus and the ventricle here, and merely just creating a line of ablation across this while evaluating contact and looking at lesion formation is good enough. But very rarely in cases like a Senning's procedure, the same cavo-tricuspid isthmus now gets bifurcated by the baffle, and this can be very clearly visualized. Moving on from there into the outflow tracts, which are crisscross. Typically, in a normally related great arteries, both the outflow tracts cannot be seen parallel to each other. Here it is the aorta or the aortic root in cross section, along with the RVOT and the main pulmonary artery in longitudinal section. This is the posterior wall of the RVOT, which shares the wall with the right coronary sinus of Valsalva. Again, this is the anterior wall of the RVOT, which can be visualized at the time of ablation, especially when trying to ablate above the pulmonary valves in order to assess for contact and quickly figure out complications. We can also see that above the pulmonary valve, we are in close contact with the left coronary sinus of Valsalva and therefore close to the left main coronary artery. Thus, these views also help us assess the safety and allow us to kind of think about possible damage to nearby structures. Similarly, here we have this view which we had seen earlier, the aortic cross section along with the left atrium, probably being able to see the appendage, and this is the right ventricular outflow tract continuing as the main pulmonary artery. Now, very rarely we get these LV summit PVCs, which we are able to ablate from an intracardiac location just below the left coronary sinus of Valsalva. This is how that location looks, the candy cane appearance below the root of the aorta protruding into the LV. This is the septum. This is the location just posterior to the mitral valve where energy can be delivered and lesion formation can be monitored. A corresponding fluoroscopic image is seen this way where this detailing is not present. Additionally, we can also use it to figure out where it is that we are on the cavo-tricuspid isthmus, especially for intracavitary structures like this prominent eustachian ridge, which will also have to be ablated, and diagnosing this prominent pouch where contact may be difficult. Also, structures like the moderator band can be visualized and assessed for contact at the time of mapping. Rarely, we might be able to see false tendons stretching across the LV cavity, which can be visualized, assessed for contact, need to be mapped in order to figure out the complete location or the possible origin of a PVC. Additional evaluations for the left ventricle start by getting the catheter into the inner or the inflow of the right ventricle, clocking from there, and as we clock we can see the moderator band, the apex of the right ventricle, and as we go on clocking from the apex of the right ventricle, we can start to see the left ventricle, especially starting from the apex, the papillary muscles, and as we clock further, we can actually see the mitral valve in the short axis. Sometimes we have intracardiac structures which are unusual. Here it is a LVAD cannula, and in this patient in whom a VT had to be ablated, it is important not only to figure out whether the LVAD is in close contact with the septum, but also guide mapping, especially during using multi-electrode catheters, and evaluate for contact with the cannula, as also the base of the LVAD, base of the ventricle just beside the LVAD cannula, to ensure that all locations are mapped properly. Very rarely or commonly more these days, but limited by our financial abilities, is the ability to be able to trace the endocardial border using intracardiac echo, represent it on an electroanatomical system, and thereby create intraventricular maps, or rather ventricular maps of intracardiac structures in order to assess for contact. This is a special program that allows us to visualize these separately from the ventricular chamber itself, and therefore we are able to map them well. These are stitched together using slices of the particular chambers wherein the endocardial borders are traced, and help to provide insight into where the catheter is at the time of mapping. This is an example of the right ventricle, the left ventricle, and the atria during one such procedure. This can also be used to guide in real time. For example, if we are able to trace this border here, this gets reflected into creation of a map, and then when we are mapping it for substrate, we can actually see where the substrate is on the intracardiac echo guided FAM map, and then go to that location in real time and be able to assess its significance with respect to the arrhythmia or the rhythm that is being mapped. In summary, therefore, intracardiac echo provides you with real-time feedback. It provides us with understanding on lesion assessment, anatomy assessment, clot evaluation, creation of FAM maps, especially with the help of intracardiac echo within an electroanatomical field, allows us to get an idea of the dimensions of what we are mapping and intracardiac structures before we actually map them. And there are increasing insights into how artificial intelligence can help us in delineation of these borders and thereby create these FAM maps without human intervention. Thank you for your patient listening. Happy to take questions if there are any.